Hmm. Okay. Am I live? Shit. uh, Seems like I'm live. YouTube is dumb. YouTube cannot see my live stream. I don't know why am I always my stream has to start this way that I'm checking it if it is live or not. But that's okay. Learning Arch Assembly on M1 Part 3, stream number 5. Yes, I'm live on Twitch also. And Tame Impala, shout out. Uh, Okay, and yeah, this is a book I was reading now. Today, we will continue where we were uh, learning our ARM assembly 64-bit. And yesterday, we completed first chapter and we learned about how you can store numbers in storage. There are two formats to store numbers in storage, Little Endian and Big Endian. In Little Endian, at the address with like a cell is normally of 1 byte, and you get data, uh, a little chunk, a word uh, is the amount of information you can store in a register, and that is the exact amount of information that you can fetch from the memory and do your work with. So, uh, in modern computers, a word that is a chunk of memory is more than 1 byte. It is like 4 bytes, which is a 32-bit computer, or 8 bytes, which is a 64-bit computer. So now you have 4 bytes, and there is a number you want to store in those 4 bytes. And those 4 bytes have four different addresses. So either you can store the most significant bit in the byte with the smallest address and leading up like that, or you can store the least significant byte in the lowest address and then move on with that. So these are called Big Indian and Little Indian. And now on to chapter 2. Yay. GNU assembly syntax. Yes, we did that. We did that. We did not do directives. Wait. Yes, some okay. There were four things. Labels. Uh, to pass assembly because they read the input file twice. On the first pass, the assembler keeps track of the location of each piece of data and each instruction and assign an address or numerical value to each label and symbol in the input file. The main goal of the first pass table is to build a symbol table which maps each label or symbol to a numeric value. On the second pass, the assembler converts the assembly instructions and data declarations into binary. Using the simple table, okay, main and message are two labels. We have comments, we have directives. So here, these are labels, okay, and these are directives, it seems. And these are assembly instructions and these are comments. We have four parts in assembly language and we will learn more as we move forward. What the assembler does. Listing 2.3 shows how the GNU assembler will assemble the Hello World program from listing 2.2. We did that. It said that GCC, which is the GNU C compiler. Uh, GNU C compiler, this dash O means that the output will be stored in a file named hello, and which file we want to convert is this. And if there is a .s at the end of the file, then It will create an object file first, and then it will link the object file with other object files which are required by this object file, and we will get our final binary file which we want, the GNU assembly directives. Each processor architecture has its own assembly language, makes sense, created by the designer of the architecture. Although there are many similarities between assembly languages, the designers may choose different names for various directives. The GNU assembler supports a relatively large set of directives, and some of them have more than one name. This is because it is designed to handle assembling code for many different processors without drastically changing the assembly language designed by the processor manufacturer. We will now cover some of the most commonly used directives for the GNU assembler. Okay, we will now be reading about the directives. Selecting the current section. Shit, my brain is not working. The instructions and the data that make up a program are stored in different sections of the program file. There are several standard sections that the programmer can choose to put code and data in. Okay, the program is divided into sections, and there are several sections in which the programmer can put data or code that will be executed on the data. Sections can also be further divided into numbered subsections. Each section has its own address counter. Each section has its own address counter, like program counter, which is used to keep track of the location of bytes within that section. Each section has an address counter, which is used to keep track of location of bytes within that section. When a label is encountered, it is assigned the value of current address. When a label is encountered, it is assigned the value of the current address counter for the currently active section. Each section has its own address counter, which is used to keep track of the location of bytes within that section. When a label is encountered, it is assigned the value of the current address counter for the currently active section. Okay, there is an address counter, and as the assembler encounters sections, it keeps giving the current address counter to that section and then updates the address counter so that when it encounters another section, it will give the new address to that section and all set. Shit. Selecting a section and subsection is done by using the appropriate assembly directive. Selecting a section and subsection is done by using the appropriate assembly directives. Once a section has been selected, all of the instructions and or data will go into that section until another section is selected. Okay, by selection they mean declaration, like just writing dot this or dot that section. The most important directives for selecting a section are shit. This is what they mean by selecting a section. Dot data. If I write down dot data, then the program counter will give that dot data section an address, and everything that the assembler encounters after that section will be a part of that section until it encounters another section declaration, which they are calling selecting a section. Oh, well, it is selecting a section because the virtual RAM that is provided to a program is divided into five sections. Stack at the top, then below it heap, then there is at the bottom text, then above text there is data and BSS. What is BSS? Fuck, there were I guess six sections. Yeah, six parts that the memory is divided into. Yep, one, one, two, three, four, five, six. Yep. Stack, this is a section. Heap, this is a section. It seems like uninitialized data. Uninitialized data, just int a and semicolon. It is just declared and is not initialized. And read-only data, the data that um, is a constant which cannot change but can only be read. Then initialized data, which contains data like int a equals some number and semicolon. So it has been declared and has been given a value. Then the program code. So these three sections can be considered a single section data, and it has, well, for me mentally it is better to remember it this way, that the data uh, can be in three parts. BSS, I do not know why this is called BSS. RO, read only data, and then data. Why is this called BSS? In in we have a section which stores the data which is not initialized. But why is it called BSS? The BSS section in memory stands for block started by symbol. Block started by symbol. This name originates from early assembly language tools used on IBM 704 and other computers in the mid 20th century. The BSS section is used for uninitialized or zero initialized global and static variables in a program. Why is it called BSS? Historical context. The Romans. In early assembly language programming, the term block started by symbol was used to define memory blocks for uninitialized variables. This term for okay, block is started by symbol. This is what someone would call to define memory blocks for uh, uninitialized variables. This terminology was coined by the United States Air Force team by Roy Nutt. That is nutty. Over time, the abbreviation BSS stuck, even though the meaning of the section has evolved. What BSS does. When a program is loaded into memory, the BSS section is allocated but not explicitly initialized in the binary file itself. Instead, at runtime, the loader or operating system initializes it to zero. This design saves space in the binary as the .bss section doesn't store the actual data, just information about how much space needs to be allocated. Yep, into this, stored in BSS, uninitialized static variable, uninitialized global variable. Test text section contains executable instructions. Data section contains uninitialized global, static, or static variables. .bss section contains uninitialized global slash static variables. Okay, so the .bss section stands for block started by symbol, which probably means that by a block they might mean a chunk in memory which was started by a symbol, not by a value, but only by a symbol like int global var. It initialized this symbol initialized uh, this symbol started or took or reserved some space in the memory. This space did not started because there is some value to be stored in there, but of this symbol, because of this symbol. This symbol took some space that might be used in future in the program. Makes a little bit of sense. Yeah, makes quite a bit of sense actually. But when it is compiled in the binary, it is not stated. It is not these uninitialized variables are not initialized to zero. It is just stated that we need this many variables of this type, and they will need this much space. That is what is written in the binary. They are not initialized to zero. But when the program executes, it sees that this much of memory is to be reserved for variables that are non-initialized, and that much of memory is stored. That much of memory is reserved in the .bss section of the program. .bss block started by symbol. Read only contains constants. Data. So moving on. Uh, yep, yep. What do we know? The memory that a program is allocated is divided into six parts. At the top, we have the stack, which grows towards the bottom, and below the stack, we have some empty space, and then below that, we have heap, which grows upward. The stack stores data that requires ordering, like recursively calling a function or call stack, things like that, which require order, right? Well, you could say that an array also requires an order, but an array will be stored in the heap because you have, let's say, initialized two arrays, but they can be stored individually. Inside an individual array, the elements are need to be stored in order, but if you initialize two arrays, they can be stored anywhere. They do not require an order. Right? They can be stored far apart, close with each other, one behind the other, anyway, right? That does not require order. So they will be stored in heap. Heap is required to give dynamic memory to the program. Maybe the array will not be stored in a heap, it will be stored in the data section. But okay, and these things will be cleared as I read more and understand more. But then below the heap, we have .bss section, which stands for block started by symbol, which stores, which is the memory allocated for the variables which have not been initialized and have only been declared. And below the .bss section, we have dots, whatever. We have .ro data, read only data. It is memory reserved for the variables which are read only, right? Which are constants whose value you cannot change. And then below that, we have the data section, which contains variables which have been declared and initialized, which contain a value. And then below that, you have the text, which stores the instructions themselves. Well, that is a mouthful. Mm, Selecting a section and subsection is done by using the appropriate assembly directive. Okay, directives are used to select a section, and then below the directive, there is the text that is supposed to go in that section. Uh, this might be wrong, but makes sense. Once section has been selected, all of the instructions and or data will go into that section until another section is selected. The most important directives for selecting a section are .data subsection, .data subsection, subsection. Oh yeah. Instructions. The instructs the assembler to append the following instructions or data to the data subsection numbered subsection. Okay, numbered to the data subsection numbered subsection. Okay, to the data subsection. to a subsection inside the data section, and whose name will be subsection. Very non-confusing. If the subsection number is omitted, it defaults to 0. This section is normally used for global variables and constants. For global variables and constants which have labels. Okay, data in memory. Dot text subsection tells the assembler to append the following statements to the end of the text subsection numbered subsection. If the instruction number is omitted, subsection number 0 is used. This section is normally used for executable instructions. .pss section, short for block started by symbol. Short for block started by symbol. Section is used for defining data uh, storage areas that should be initialized to 0 at the beginning of the program execution. The .bss directive tells the assembler to append the following statement to the end of the BSS subsection numbered subsection. If the subsection number is omitted, subsection number 0 is used. This section is normally used for global variables which need to be initialized to 0, regardless of what is placed into the section at compile time. All bytes will be set to 0. Okay. When the program begins executing, this section does not actually consume any space in the object or executable file. It really just uh, it is really just a request for the loader to reserve some space when the program is loaded into memory, right? Just like we discovered. Section name. In addition to the three common sections, the programmer can create other sections using this directive. However, in order for custom sections to be linked into a program, the linker must be aware of them. With the GNU tools, this can be accomplished by providing a linker script. That topic is outside the scope of this book, but interesting readers are referred to the GNU linker documentation. Allocating space for variables and constants. There are several directives that allow the programmer to allocate and initialize static storage space for variables and constants. There are several directives that allow the programmer to allocate and initialize static storage space for variables and constants. The assembler supports bytes, integer types, floating point types, and strings. Okay, supports bytes. We can store bytes, integer types, which is stored as bytes, floating point types, which are stored as bytes, and strings, which are stored as bytes. But we do not have to provide their byte form. We have to provide them as integer, float, or string, which will be converted into bytes. And that is cool and reassuring. These directives are used to allocate a fixed amount of space in memory and optionally initialize the memory and optionally initialize the memory. Yeah, we don't have to initialize. We can just ask for memory space and then not use it. Some of these directives allow the memory to be initialized using an expression. An expression can be a simple integer or a C style expression. The directives for allocating spaces are storage are as follows. Hmm. Byte, byte expressions, dot byte expects 0 or more expressions separated by commas. Okay, each by using an expression to be initialized by using an by expression they mean the name for that storage. Okay, this will all become more clear when we actually write programs, right? Uh, okay, dot bytes expects 0 or more expressions separated by commas. Each expression produces 1 byte of data. Each expression produces 1 byte of data. The first byte is placed at the current address counter, and then the counter is incremented so that the second expression is placed at the next byte, and so on. If no expressions are given, then the address counter is not advanced and no bytes are reserved. Okay, expression is the value that we want to store there. Okay, dot 2 byte, half word, dot short word, shit, dot short expressions. For AArch64 processor, these directives all do exactly the same thing. They expect zero or more expressions separated by comma and emit a 16-bit number. Emit a 16-bit number for each expression. If no expressions are provided, then the address counter is not advanced and no bytes are reserved. And emit a 16-bit number. 2 bytes, 16-bit. Half word, 16-bit. But we are using a 64-bit processor, then the size of a word should be 16-bit. Should be 64-bit. Short. Okay. If no expressions are given, then the address counter is not advanced and no bytes are reserved. Dot 4 bytes, 32-bit. A word is of 32-bit. Okay. For AArch64, these three directives do exactly the same thing. They expect zero or more expressions separated by commas and will omit 4 bytes for each expression given. If no expressions are given, then the program counter is not advanced and no bytes are reserved. Dot 8 byte, quad, which is a 64-bit thing. For R64 processors, these two directives do the same exact thing, do exactly the same thing. They expect zero or more expressions separated by comma, 8-bit, and program counter does not, address counter does not move on if no data is provided. ASCII string. We provide a string in brackets in these double quotes in under this .ascii directive, which will store the string. The .ascii directive expects zero or more string literals, each enclosed in quotation marks and separated by commas. It assembles each string with no trailing ASCII null character, into consecutive addresses. ASCII dot string. The .ascii directive is similar to the .ascii directive, but each string is followed by a ASCII no character. The Z in ASCII stands for zero. Oh, ASCII is a dot string is just another name for ASCII. Okay, equivalent is static variable declaration in assembly and C. Static int I equals this. Okay, what would be the assembly form for this? It would be under dot data, we get I. Oh, okay, okay. Is this the format how we define things? Okay, by this I give it a name, and this is what I want it to be. Okay, and how was the hello world program? Okay, we had .msg something section, section dot read only data section. Okay, in which we had a thing called message, which stores an ASCII, and this is the value of the ASCII. Then the dot text section, which means this is the main code, store this in the text section. Then dot global main, which will mean something, prints hello world and returns zero. Strip, okay, strip, okay, we will know this in due time. Dot float numbers, dot single. This directive assembles zero or more floating numbers separated by commas. Oh, this will store the address of the first thing. So this is the address for the first thing because these are stored line by line. Oh, this is the equivalent to something we called an array. In AArch64, they are 4-byte IEEE standard single precision numbers. Dot float and dot single are synonyms. Dot double float numbers. Okay. Float stores 4 bytes and double stores 8 bytes. Full 64-bit register utilization. Okay, figure 2.1. This shows how these directives are used. Mhm. Voice is low. Voice is low. Figure Figure 2.1 shows how these directives are used to declare variables and constants. Figure 2.1b shows the equivalent statements for creating global variables in C or C++. Oh, this is the same syntax used for C++, I guess. Note that in both cases, the variables created will be visible anywhere within the file that they are declared, but not visible in other files which are linked into the program. Okay, they will be visible everywhere in this current file, but not anywhere outside this file. In C, the declaration of any array can be performed by leaving out the number of elements and specifying an initializer as shown in the last three lines of figure 2.1b. In C, the declaration of any array can be performed by leaving out the number of elements and specifying an initializer and as shown in the last three lines of C by leaving out a number. FMT. FMT, friends most trusted. Okay, character array, char array, integer array. Yep. In C, the declaration of an array can be performed by leaving out the number. Leaving out the the grammar does not seem to be grammaring. By leaving out the number of elements and specifying an initializer as shown in figure in the last three lines. In assembly, the equivalent is accomplished by providing a label, a type, and a list of values that makes direct sense, as shown in the last three lines of figure 2.1a. The syntax is different, but the result is precisely the same. Listing 2.4, shit, from 1 to 2.4. Wait, literally from 1 to 2.4. Oh, this is the listing. This was figure. Listing 2.4 shows how the assembler assigns addresses to these labels. The second column of the listing shows the address in hexadecimal that is assigned to each label. The variable I is assigned the first address. Address counter starts at a place in the memory. Okay, I will have to read about address counter. Okay, the first for I get this. For J, I get this. For FMT, friends most trusted, I get this. Whose address starts at this and it contains two things. Shit, crazy. Wait, but how does this contain hello world in only this much space? ASCII uses 5, 6, 7, 8 bytes to represent one character. So how does only 2 bytes amount to this much? One, 2, 3, 4, 5, and 6. And we have here 8, 9, 10, 11, 12, 13, 14. 14 and 6. How is this stored in this? Uh, ah, shit, shit. Should I hide my screen? No. Inquiry.jatin Raghav. Inquiry.jatin.raghav@gmail.com. You can contact me there if you want. This is a line in the data section. Uh, how will this hello hello \n string be stored in the memory because uh, it uses the wait, yes, there is z at the end of this. Therefore, uh, this end two characters mean null, right? So, did I misread what the uh, this does dot asciies does? Is directive is similar to the .ascii directive, but each string, no way, expects zero or more string literals, each enclosed in quotation marks and separated by a comma. It assembles each string with no trailing ASCII null character in consecutive addresses. Okay, so it just says that whatever is provided in double quotes will be stored as ASCII characters, and ASCII characters take 1 byte because 256, 1 byte. And it uses .as is directive which stores the provided string as which stores the provided string as ASCII, and ASCII uses 1 byte to store a character. So uh, and because this is dot ASCII's, it will also have a null character in the end. Therefore, will it take 7 bytes to store the whole string? Yes, you are correct. When the .asciies directive is used in the .data section, it stores a string. Section to store a string, it stores the string as ASCII characters, with each character taking 1 byte. I am fucking stupid. Yes, I am stupid, it seems, because 1 byte, that is 8 bits, that is 256, can be expressed using just two hexadecimal characters. Stupid, yes. And appends a null terminator at the end. Let's break it down for you. But it should still use 8 bytes. And is it using 8 bytes? It is started at 8. This one used how much? 4, 1, 2, 3, 4, 5, 6, 7, 8. This one, this one used 8 bytes, and they are not representing them as like 4 bytes because that would They are not representing these values as bytes in binary because it would take 32 single digits to represent them. So here in this context, they are using hexadecimal to two hexadecimal characters to represent one byte of information. So this should take, as I said, 7 bytes. Yes, it should take 7 bytes. So if I add 7 to 8, or to get 15, and 15 is represented by F. So yes, hypothesis works out. Each character takes 1 byte to be stored, and that byte, that single byte, is represented as by two hexadecimal characters here. Okay, I was not stupid. Well, I am, but okay, works out. Memory layout. The strings will be stored in memory as this. How will they be stored as this in the memory? Okay, so they really won't be stored as hexadecimals, right? You are just using hexadecimal here to represent them concisely. Mm, but in the actual memory, they will be stored as 32 bits. That is that is 32 zeros and ones. You are absolutely correct. In memory, the characters are not stored as hexadecimal values per C per se. Hexadecimal is just a human readable representation used to make it easier to interpret binary data. In reality, each character is stored as 8 bits, 1 byte in memory, representing its ASCII value. These 8 bits are binary values. Yes, that was wrong to say 32 bits. Uh, yes, that was wrong to say 32 bits. Each character is stored as 8 bits, 1 byte in memory, representing its ASCII value. These 8 bits are binary values, combinations of zeros and ones. For example, the string hello with ASCIIs would be stored as memory in memory as follows. Okay, this will be stored as this, E will be stored as this in binary. Okay. Clarifying 32-bit memory. With the native word size of your PC, example 32-bit or 64-bit, may define how much data it processes in one operation. It doesn't change how strings are stored in memory. Each character in a string is still stored as bytes. If your streaming line memory aligns memory for performance, example on a 32-bit or 64-bit boundary, the compiler might add padding bytes to align data, but this does not change the fact that each character is fundamentally represented by 8 bits. That makes sense. Okay, filling and aligning. Padding to align. 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 Okay. On AArch64 CPU, data can be moved to and from memory 1 byte at a time. 1 byte at a time, 2 bytes at a time, that is a half word, 4 bytes at a time, that is a full word, or 8 bytes at a time, double word or long. Oh, that is why they call it double, because it is double word. Okay. Moving a word between the CPU and memory takes significantly more time if the address of the word is not aligned on a 4 byte boundary. If the address, okay. If the address of a word is not aligned on a 4 byte boundary at the interval of 4, okay. One where the least significant 2 bytes of these address are 0. One where the least significant 2 bytes, least significant 2 bits of the address are 0. Least significant 2 bits of the address are 0. Wha- Okay. Uh, a word is a 32-bit long container which contains 32 bits, and its address is specified using its address is specified depending on the m- size of the bus. If the bus is the size has the same size as the word, then 32 bits will be used to store the address of of the location in the memory. But here, one where the least significant 2 bits of the address are 0. So there is a string of zeros and ones which are used to represent the address of a cell in memory. And if the least two significant bits are 0, which means if these are 0, then the number one where the least two significant bits of the address are 0. Okay, if the least two significant bits are 0, then the number, is it always a multiple of 4? There is a question. Let's see. Least two significant. It seems like it is, because if these least two significant bits are 0, then this might be 0 or this might be 1. And either case, this will be a multiple of 4, because if this is 0, then let's say there is something we don't care, but let's say there is something actually there, then it will be a multiple of 4. And because multiplying, because the next digit only represent twice the last one. So if we have anything after this 0, which represents 4, then this will be 8, which is twice of 4. This will be 16, which is twice of 8. This will be 32, which is twice of 16. And all of these are multiples of 4, right? So, yeah, if the last two bits are 0, then it is a multiple of 4. And why only the last two bits? Because the third bit is used to represent 4 itself. Crazy. Similarly, moving a half word between the CPU and memory takes significantly more time if the address of the half word is not aligned on 2 byte boundary, when where the least significant bit of the address is 0. And moving a double word takes more time if not aligned on an 8 byte boundary. 8 byte boundary, one where the last where the least significant, how many? For 8, least 3 significant bits, 3 bits of the address are 0. Therefore, when declaring storage, it is important that double words and half words are stored on appropriate boundaries. The following directive allows the programmer to insert as much space as necessary to align the next item on any boundary desired. Okay, and I think the reason that takes much more time to fetch a value from the memory if it is not properly aligned is because it is designed that way for optimizing reasons. The people who build processors, or more correctly, RAM, the memory, make them so that it is easier for them to fetch data from boundaries faster. Okay. And this is used to align things. Dot align abs abs expression. Makes sense. Pad the location counter. Okay, pad the location counter in the current subsection. Pad the location counter in the current subsection to a particular storage boundary. For the AArch64 processor, the first expression specifies the number of low order 0 bits location counter must have after advancement. Uh, 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 okay. The second expression gives the fill value to be stored in the padding bytes. It and the comma may be omitted. And the comma may be omitted. If it is omitted, then the fill value is assumed to be zero. The third expression is also optional if it is present. It is the maximum number of bytes that should be skipped by the alignment directive. Okay, this is used for alignment, for aligning, for like if the value that you want to store in a 32-bit memory location is less than 32, then it is used to provide a buffer of zero or alignment padding, as you might call it, to make it a 32-bit value. But that is the theoretical reasoning for this expression. But what does it mean? Okay. Uh, pad the location counter. Pad the location counter in the current subsection. Okay. There will be a subsection below this expression whose and the program counter, the location counter, address counter will be padded in that to a particular storage boundary. For the AArch64 processor, the first expression specifies the number of low order 0 bits the location counter must have after advancement. Mm, The number of 0 order bits the location counter must have after advancement, that does not make a lot of sense. My brain is not working, even though it is just morning. Okay, this will make sense, I guess, with time. One of those things. BA align. But I get conceptually what it means. It means to get, it is there to align values to take proper spaces as the memory would expect a value to take. Dot BA align. B align. LW expression, abs expression. Okay, these directives adjust the location counter to a particular storage boundary. Adjust the location counter. Adjust the location counter to a. Oh, fuck it. Uh, what is a location counter? And my hypothesis. My understanding uh, is it a register in the processor which keeps the address for the first memory location of the virtual memory that is allocated to a program, and as it encounters more and more data that needs to be stored in the memory, uh, uh, it is used to uh, get the address to store the data and, and store the data that the assembler encounters and the then this address counter is incremented according to the amount of data just stored and is used again when the when another when the next chunk of data is encountered. Allocation counter is not a hardware. Allocation counter is not a hardware register in the processor, rather than it is a logical concept used by an assembler to track memory address during the assembly process. It is a part of the assembler's internal bookkeeping. Okay, it is like it is used by the assembler. Conceptual thing which is used by the assembler. Purpose of location counter. The location counter is used to first keep track the current memory address being assigned to instructions or data during the assembly of a program. Okay. Assign address to labels, data, and instructions as they are processed by the assembler, which is okay. Ensure that memory addresses are correctly incremented based on the size of each instruction or data item. That makes sense. How it works. Initialization. When the assembler starts assembling a program, it initializes the location counter to the starting address of the memory segment being processed. Example.text.data. Incrementing as the assembler processes each instruction or directive. It uses the value of the location counter as the address for the item. After assigning the address, the location counter is incremented based on the size of the item just stored. Example, 1 byte for a byte, dot byte directive, 4 bytes for a 32-bit instruction, etc. Labels. When the assembler encounters a label, it associates the current value of the location counter with that label. This way, the label acts as a symbol reference to that memory address. When the assembler encounters a uh, label, label like name, it associates the current value of the location counter with that label, so then that label can be used to refer to the address of whatever is stored, whatever is provided under that directive. Okay, there is something that I don't get. Initialization. So, what address does it initialize at? Is it the first address uh, in the virtual memory that is provided when the assembler starts assembling a program? It initializes the location counter to the starting address of the memory segment being processed. Here's how the location counter might behave during the assembly of a simple program. Not data. This location encounter this is assigned address this. Location counter is this, and y is assigned the address this, and this is this, which is assigned the address this. Hello takes 7 bytes for 7 bytes, one for the null, for 6 byte for character, one for the null location, and counter is this after 0, and okay, new text. Okay, location counter to this in the dot text section. It switches. Okay, okay. 4 byte instruction. Location counter is add this after the instruction. So it switches between sections, and each section has its own memory assignment which starts at 0. And how does that work? Well, of course, this is not the address of the physical memory that is being used. This is, of course, the virtual one. But is the virtual one itself divided into 6 sections, like not just conceptually, but literally divided into 6 sections, which correspond to different to the conceptual 6 sections onto the physical memory. Let's see. The location counter is not a physical register in the CPU. It exists only during the assembly phase, managed by the assembler. Its purpose is to assign memory addresses and track where the next piece of data or instructions should be used. In the final executable, the memory address assigned by the location and counter during assembly is used for proper linking and loading. Relation to virtual memory. The location counter has no direct connection to the virtual memory or the program's memory allocation during execution. It operates in the assembly phase, and its purpose is purely to assign and manage symbolic memory addresses. The program loader later maps the assembled instructions and data onto the virtual memory of the processes where the program is executed. Okay, when assembling, where when assembling the address that is stored in the location counter is just a representation which will be used to assign addresses to uh, text or data in sections, and each section. Okay, and after assign, what is the spelling for assigning? ASSIGN. Assigning the addresses. After assigning the addresses, uh, these addresses will be mapped onto the virtual memory. And does the location counter uh, starts keeps a uh, separate state for all the sections it encounters. Correct understanding. Okay. Yes, you are correct. During assembling, the address stored in the location counter is a representation used to assign addresses to labels, instructions, and data with the different sections. Example.txt, data, BSS. Block started by symbol. Shit, I forgot. So stupid. These addresses are typically relative to the start of their respective sections. Hmm. Later during the program's execution, the linker combines object files resolves symbols and determines the final memory layout. The loader maps these. Okay, the addresses provided by the program location counter will be stored in the loader, but when the loaded object files Now, what the fuck is loader? The loader maps these addresses. Linker combines the object files, resolves symbols, and determines the final memory output. The loader maps these addresses onto the virtual memory allocated to the program by the operating system. Loader works when the program has started executing. It loads the instructions into the memory, and linker combines the object files. Okay, the address is tracked by the assembler, are not the final physical or virtual addresses, but are used as blueprints for the memory layout. That makes much more sense. Does the location counter keeps separate states for each section? Yes, the location counter maintains a separate state for each section. Here's how it works. Each section has its own location counter. For example, .text, .data, .bss section has its own location counter to track instruction addresses. Okay, and there are things why separate counters. Different sections of the program are often loaded into different regions of memory, but they are provided as one part to the program in the virtual memory. The assembler needs to keep track of the memory layout within each section independently to assure proper alignment and address assignment. Switching between sections when the assembler encounters a directive like .text, it updates the current location counter to the appropriate one for the section. The assembler encounters that symbols within a section are relative to the section's starting address. Yeah. Separate location counters. Here is a small assembly program illustrating how the assembler might manage location counters. It initializes a new location counter at 0 in the section text. Location counter for .text starts at 0. Address stores 4 byte, stores 4 byte. An instruction takes 4 bytes. That is crazy. 4 bytes. 4 bytes. How are these 4 bytes divided? Okay, okay. Data section. Initialize a new location counter at 0 for the data section and does its thing and BSS. That makes sense. Virtual memory mapping. When the program is loaded into memory for execution, each section is loaded into a separate segment into the program's virtual memory space. Read-only executable, one region of virtual memory, another region of virtual memory, another region of virtual memory. The addresses is assigned during assembly becomes relative offsets within the respective section. The loader calculates the final virtual addresses by assigning the section's base address determined by the operating system to these offsets. Conclusion: the location counter is a tool used by the assembler to assign symbolic addresses within each section of a program. Each section this has its own independent location counter. During execution, these addresses are mapped into the program's virtual memory by the loader, ensuring each section resides in the appropriate memory segment. That makes sense. And I'm very live in Twitch. Very spontaneous, I would say. And it's been 1 hour
Let's
in
see
the
how.
appropriate memory segment. Fuck. I'm like, latency is really high in YouTube. I don't know why. Well, this would work. At least it is not, it is lagging. It is not getting stuck, at least. Yo, Technoblade never dies. Okay, what's that? Logged out. Okay, now. Hmm, 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 hmm. I know what the program counter is. Now, pad the location counter. Shit, it is going to take an eternity to understand all this. Okay, I have to create a target. That is the amount that I will do, at least do. Ah, where is the index? Okay, GNU assembly syntax, assembly directives. Here I am. Uh, this is the last topic. Okay, but I warn you, I'll break your heart. Already broken. Okay, I did this. Huh? Maybe I can do this whole part, like instructions part. And that is going to be the target. Crazy, but okay. Uh, yes, yes. Pad the location counter in the current subsection to a particular storage boundary. This will make sense later, I suppose. These directives adjust the location counter to a particular storage boundary. The first expression in the byte multiple for the alignment request. For example, dot byte multiple for the alignment request. Yo, Mark Norman dot B align 16 will insert fill bytes until the location counter is an even multiple of 16. Oh, is an even multiple of 16. That makes more sense than what was there before. If the location counter is already a multiple of 16, then no fill bytes will be created. That makes more sense. The second expression gives the fill value to be stored in the fill bytes. That makes sense. It and the comma may be omitted. If omitted, then the fill value is assumed to be 0. The third expression is also optional. If it is present, it is the maximum number of bytes that should be skipped by the alignment directive. B align W, align W or L, and B align L directives are variants of the B align directive. The B align W directive treats the fill pattern as 2 byte words value, and B align L treats the pattern fill pattern as 4 byte long word value, as 2 byte word value and 4 byte long word value. For example, this will word this every space that this skips 4 bytes, and we have given it 2 bytes. Therefore, if the amount of memory that needs to be skipped is 3 bytes, let's say, then this value will be stored in the 2 bytes and the remaining of byte will have 0. Will align to a multiple of 4 bytes. If it skips 2 bytes, they will be filled with the value this. The exact placement of the bytes depends upon the endianness of the processor. Little endian, big endian. Skip size fill, space size fill. Sometimes it is desirable to allocate a large area of memory and initialize it to the same value. This can be accomplished by using these directives. These directives emit bytes, size bytes, each of fill value this. Both size and fill are absolute expressions. If the comma and fill are omitted, fill is assumed to be 0 for the ARM processor. The dot space and skip directives are equivalent. This directive is very useful for declaring large arrays in the .bss section. Uninitialized, we can using fill. Listing 2.5 shows how the code in listing 2.4 can be improved by adding an alignment directive at line 6. Where is listing 2.5? We have this. Where did we go? Yo. Wow. Listing 2.5 shows how the code in listing 2.4 is 2.4. There is 2.5 where we can put align dot align 2 here, and this will be used to align this. Okay. And now that we have aligned this, these 0, 1, 2, 3, 4 take full byte, full 8 bytes. They take full word size. And what is 2? 2 is, don't know what the fuck is 2. And see, this, the most significant bit is stored in the smallest address. This is small endian. Taking notes. Okay. The extra listing 4 can be improved. And if we go up there at listing 2.4, we see the same thing. Misaligned data. How is this? Wait, this is at 12, and that is okay. This has double zeros here. This takes 2 bytes here. Why are 2 bytes here? Well, okay, so why are here 2 bytes? Why are 2 bytes here? Pad the location counter in the current subsection to a particular storage boundary. For the AArch64 processor, the first expression specifies the number of low zero order bits the location counter must have after advancement. Yep, back. Atom. Wait, this seems to be lagging. And what about YouTube? Doesn't even know what the heck is going on. YouTube is also lagging. Okay, shit, this is bad. Why does it keep lagging? Well, we have our target. Let's go. I do not get the line thing. Uh, why is he saying that this one is misaligned and that this one is aligned? Why? Okay. Uh, 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 uh. This made 2 bytes skip. Why did it do that? The first expression specifies the number of low zero bits the location counter must have after advancement. The second expression gives the fill value to be stored in the padding bytes. The fill value to be stored. The second expression gives the fill value to be stored in the padding bytes. The fill value, the fill value to be stored in the padding bytes. Okay, it and the comma, it and the comma may be omitted. If it is omitted, then the fill value is assumed to be 0. The third expression is also optional. If it is present, it is the maximum number of bytes that should be skipped by this alignment directive. We use to skip a specific number of bytes when the location counter and encounters it. Technically, the align directive is used to align the location counter to a specific boundary, which often involves skipping a number of bytes. However, the purpose of dot align is not directly to skip bytes, but rather to ensure that the next data or instruction starts at a memory address that is a multiple of a given alignment. So, okay, that makes a little sense. Okay, so why did it do two? Two means, what does two mean? Two means, what the heck does two mean? Uh, how was it here? Is that the only change? Yep, that seems to be the only change. And if 2 means 2 bytes, then well, 12 was a multiple of 2, not 12. Wait a minute. Uh, well, it increased by 2 when you specify 2, and if 14 is supposedly on the boundary of at the boundary of a multiple of 2, then 12 should also be there, right with it. The line directive, okay. However, the purpose of a dot align is not to skip bytes, but rather to ensure that the next data or instruction starts at a memory address that is a multiple of the given alignment. How dot align purpose? The dot align ensures that the current location counter is adjusted so that it is divisible by the specified alignment boundary. It was not 12, it was 1, 2, which in hexadecimal means 10 is F, 10 is 16, 11 is 17, and 8. 12 is 20, and 13 is 21, 14 is 22. So if 20 is also a at the boundary of 2, right? Skipping bytes. If the current location counter is not already aligned, the assembler skips the necessary number of bytes by inserting padding bytes, usually zeros, but this can vary depend. Okay, alignment value. The alignment value is typically specified as a power of 2. Oh, power of 2. That is how it is specified. Okay, as a power of 2. So 2 means 2 power 2, 4. So therefore, but 1, 2 is 20, which is a power of 4. Aligns to byte dot y. X is stored as a byte. Therefore, it takes one location. Okay, okay, okay. It makes sense now because 20, uh, well, 20 is not at the boundary of 4. Why? Because the address starts at 0. So 0 is the first address, 1 is the second address, 3 is the 2 is the third address, and 4 is the fourth 3 is the fourth address. As 3 is the fourth address, then 4 should be at the boundary. 0 is the first. At second we have 2. At third we have second. At fourth we have third. and then 4 is the first, next first. Then we have 5, 6, 7. Then 8 should be the one. Math is not mathing. 0 is the first address. It is at the boundary. It is correct. Then we have 1, address 2, address the fourth, address 3, which stores the fourth byte. And if we want to align, okay, starts at address 0, okay, dot by 4 bytes, align to 4 byte boundary, and this is the value. This is what you want, align to 4 byte boundary. Then what this should it should increase the program counter by storing 3 bytes of data, because 1 byte is given here and we have 3 bytes. And if we skip the 3 bytes, then we supposedly have stored 4 bytes of data, the resulting in 3 bytes of data inserting. And y is placed at 4. Example 2, align without padding needed. Z is stored as a byte, starts at 0, no padding needed, since this is already a 4 byte align. Is aligned at starts at address 4. Okay, if the location counter is already aligned, it does not encode the exact same code for from before. Oh, okay, that makes sense. Therefore, the math was mathing. This is aligned by 4 bit. This is aligned by 4 bit. This is aligned by 4 bit. And okay, okay, is 1 2 aligned by 4 bit? What is 1 2? 1 0 is 16 in hexadecimal. Okay, stupid. 1 0 is 16 in hexadecimal. 1 1 is 17, and 1 2 is 18. 18 is not at the boundary of when you have 4 bytes. Therefore, we added 2 bytes to get to 20, and 20 1 4 is 20. So that makes sense. Okay, that makes sense. Right. Listing 2.5 show that took quite a bit of time. 9/11, exact bombing time. Listing 2.5 shows how the code in listing 2.4 can be improvised by adding an alignment directive at line 6. The directive causes the assembler to omit 2 0 bytes between the end of the ch character and the beginning of the array variable. These extra padding bytes cause the following word data to be word aligned, thereby improving performance. When the word data is accessed, it is good practice to always put an appropriate alignment directive when the size of the data on the next line is larger than the size of the data on the current line. Yes, for example, if the previous line declares a byte half word, string byte half word, or word data, and the current line declares uh, double word, then an align 3 directive should be placed between them. Likewise, if the current line declares word data and the previous line declares string byte or half word, then line 2 should declare it. Directive should be placed between them for a line declaring half word data following a line declaring string or byte data. And dot align 1 directive should be placed between them. Go to setting and maintaining symbols. Okay, okay, I get this. I get this. I get this much. is much like the aligning part. I get now. I get the aligning part. I get the program counter part. But I do not get when the oh no, it is all in one section. It is all in data section. That is why the program counter is always does not changes to zero when it encounters a new directive, because these directives are subsection smaller directives whose values will be stored in the .data directive. Yeah, yeah. The assembler provides support for setting and maintaining symbols which can then be used in other places within the program. The labels that can be assigned to assembly statements and directives are one type of symbol. One type of symbol. The programmer can also declare other symbols and use them throughout the program. Hmm. Such symbols may not have an actual storage location in memory, but they are included in the assembler's symbol table and can be used anywhere in there that their value is required. The most common use for defining symbols is to allow numerical constants to be declared in one place and easily changed. The .eq directive allows the programmer to use a label instead of a number throughout the program. And this contributes to readability and has the benefit that the constant value can then be easily changed every place that it is used just by changing the definition of the symbol. The most important directive related to symbols are this. Okay, instead of using directives, we can use symbols. This directive sets the value of the symbol to expression. It is similar to C language. Define directive. Define directive. Hmm. EQUIV. What is IV? Well, IV is baby. Dot EQUIV directive is like dot EQ and set, except that the assembler will signal an error if the symbol is already defined, like unique or something. Global and then global global. This directive makes the symbol visible to the linker. Okay, if the symbol is defined within a file, and this directive is used to make it global. Then when it will, okay, global underscore main. When we write in assembly, this directive makes the symbol visible to the linker. Makes the symbol visible to the linker. Okay, the linker can see and link it to different files. It can be called from outside the file. If the symbol is defined within a file, if the symbol is defined within a file and this directive is used to make it global, then it will be available to any file that is linked with the one containing the symbol. Okay, this is like export. Without this directive, symbols are visible only within the file where they are defined. Defining a symbol for the number of array. Okay, inside the dot data directives, we have I, which is store, which has type, which has length word, stores 0, and this one stores 1. FMT, uh, mm, friend, most trusted. This stores this, and then we have this, and this. Then at the end we have, okay, dot EQ. What does this do? Array size. What it does, it stores array size. Uh, it declares that we can use array size. Uh, 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 Array size. This is 5. This is 5. Why is this 5? What does this expression? D2 is this expression which will be calculated easily normally. Uh, Dot. Okay, dot minus array divided by 4. Dot is the current location of the program counter, it seems, right? So the current location after this, I took 5 5 uh, each thing each thing takes 4 bytes. It is a word, right? So 4 4 4 4 4 20 bytes. This should be increased by 20, but this is hexadecimal, so do not add 20. It does not mean you can add you can make this write this as 34 after adding 20. It is hexadecimal. The math is does not math in the same way. So this means this the current location of the location counter minus the location of this, which is the starting, and then divide that by 4. Why 4? Because each memory location is of size 4. We get 5. Hmm. Linked. Yeah. If the symbol is defined within a file and the directive is used to make it global, then it will be available to any file that is linked with the one containing the symbol. Without this directive, symbols are visible only to the file within that they are defined. Okay. Dot common symbols and length. This directive declares symbols to be a common symbol. Declares symbol length. Declares symbol to be a common symbol, meaning that if it is defined in more than one file, then all instances should be merged into a single symbol. Is only in one file, the linker will allocate length bytes of uninitialized memory. If there are multiple definitions of symbol and they are have different size, then the linker will merge them into a single instance using the largest size defined. That makes sense. Listing 2 and 6 shows how the EQ directive can be used to create a symbol holding the number of elements in an array. The symbol array size is defined as the value of the current address, denoted by the dot, minus the value of the array symbol divided by 4. Each word in the array is of 4 bytes. The listing allows all the symbols defined in this program segment. Hmm. Note that the 4 variables are shown to be in the data segment. Note that the 4 variables are shown to be in the data segment, and the array size symbol is marked as an absolute symbol, which simply means that it is a number and not an address. It's an absolute symbol, which means that it is a number, not an address. It will have no storage location in the running program, but it is a value. Its value can be used wherever needed while the file is being assembled. Okay, okay, while the file is being assembled, the programmer can now use the symbol array size to control. It is for the program. It is like React. It is like React for the programmer experience. The programmer can now use the symbol array size to control looping when accessing the. It is like TypeScript over on JavaScript. The programmer can now use the symbol array size to control the looping when accessing the array data. If the size of the array is changed by adding or removing constant values, the value of array by adding or removing constant values, the value of array size will change automatically, and the programmer will not have to source through the code to change the original value 5 to some other value in every place it is used. That is interesting. Functions and objects. There are a few assembler directives that are used for defining the size and type of labels. This information is stored There are few assembler directives that are used for defining the size and type of labels. This information is stored in the object file along with the code and data and is used by the linker and or debugger. Dot size, name, and expression. Store this name with this expression. This The size directive is used to set the size associated with a symbol. This information helps the linker to exclude unneeded code and or data when creating an executable file and helps the debugger to keep track of where it is in the program. These things will make much more sense when I am actually writing the code. Yep. Dot type name, and it is not supposed to be read like this, like a fucking novel. It takes time, right? Writing and actually writing. I will be solving advent of code in assembly language for my practice when I am like know how to do some stuff. This is just a theory part to get an idea of how things work, right? Yep. The size directive is used to set the size associated with a symbol, and I can read this again afterwards. Yep. Helps the linker to exclude. Is that making an excuse? This information helps the linker to exclude unneeded code and or data when creating an executable file and helps the debugger to keep track of where it is in the program. Okay. Dot type name description. The dot type directive sets the type of a symbol name to be either a function or an object. Dot type directive sets the type of a symbol to be either a function or an object. This thing is this valid values for dot type description in GNU Rs assembly include function with the percentage. The symbol n is a function name. Yes, the GNU indirect function. The symbol is an indirect function and may be called through a function pointer table. Uh, Object, this is in a data object. TLS object, thread local data object, common. This symbol is a common shared object. No type, this symbol has no type. Note, some assemblers include some versions of the GNU assembler may require the character this instead of the this character. The following example shows how a typical function is declared. This type, my function, is of type function and it will be accessible outside the program. And the example of the function code goes here and size function. My function C has, wait, okay, the symbol has the size this, yo, size of the current thing and the size of this where it started. The period dot the period in the expression dot this minus my function is a reference to the current memory current counter value. The expression dot this minus this means subtract the location of my function from the current location. This directive declares. Okay, and this directive calculates how many bytes there are between the label function and the current location of the dot size directive and provides that information for the linker and other debugger so that it will know how much location this thing needs. Okay, conditional assembly. Oh, yes. If sometimes it is desirable to skip assembly of portions of a file. To skip assembly of portions of a file. Okay, so we will not convert them into binary executable code. We will not assemble based on some conditions. The assembler provides some directives to allow conditional assembly. Okay, one use for these directives is to optionally assemble code as an aid for debugging. As an aid for debugging. Okay, these will only be there for the programmer to see and will not assemble like the comments. If this also in C, if expression. if marks the beginning of a section of code, which is only considered part of the source program being assembled if the argument, which must be an absolute expression, is non-zero. If it is non-zero, then it will be assembled. The end of the conditional section of code must be marked by the dot end if directive. Optionally, code may include for the alternative condition by using dot else dot if def symbol uh, assembles the following section of the code if the specified symbol has been defined. Uh, if the symbol has already been defined, then this if not defined, symbol has not been defined, else assembles the following section of code only if the condition of the preceding if or if def was false and if marks the end of a block of code that is only assembled conditionally, including other source files. Dot include should hashtag include this that header file and C. Yeah, just like this. This directive provides a way to include supporting files that is specified at specified points in the source program. The code from the included file is assembled as if followed it followed the point of the dot include directive. When the end of the include file is reached, okay, this directive provides a way to include supporting files at specified points in the source program. The code from the included file is assembled as if it followed the point of the include directive. When the end of the included file is reached, assembly of the original file continues. Okay, it just puts the code for that file in wherever dot include is written. The search path used can be controlled with the I command line.